I'm going to do two things this morning. I'm going to start by talking about radar data, giving some background into how to use it, some of the techniques, what it does and what it doesn't do. Not all of these things are going to be relevant to understanding Venus, because the radar data we have from Venus is old, and techniques have moved on. But I thought I'd share them all with you, and maybe some of the future missions that are coming might make use of them, and it's worthwhile knowing. And some of our terrestrial data does make use of these. Lots of our terrestrial data does make use of these resources. So let me give a little bit of background. If I can get the slide to move, there we go. As to what radar is and isn't. Radar is an active sensing system, which means that the light source, if you like, for the image is created by the sensor itself. So the radar generates a pulse of energy at radio or microwave frequencies, and that illuminates the ground on the surface, and some of that energy is reflected back and received by the sensor to create an image. The way in which that information is recovered by the sensor is perhaps not something we're familiar with, and is very different to the way a camera system operates, for example. So on the receiver, as well as it's part of the same transmit-receive system, on the receiver, the backscattered radar signal is recorded in what's called in phase, which is sort of 0 and 180 degrees of the wave, and quadrature, which is the 90 to 70 degree part of the signal that comes back. So don't worry about the details, but if you look at the image on the right, the graph on the right, you'll see that the wave goes up and down, and we record two parts of that wave. And those two signals, the in phase and quadrature, can be combined in two different ways. If we square them, add them, and square root them, we get what's called the amplitude of the signal, and that's the image that we're familiar with seeing in, say, Magellan images. And if we take the arctangent to it of the ratios, then we get the phase information, which is something I'll discuss a bit later on. And at the moment, we don't really make use of that information from Magellan or any other space-based system outside of the Earth. The way that synthetic aperture radar works is by using the orbit of the spacecraft, the motion of the spacecraft, to synthesize a larger antenna than can be physically put into space. With an antenna that's only 10 meters across, for example, we would not be able to image at high resolution on the ground. We would probably, I don't know, image something like a kilometer resolution or something. So to get the really high resolution, we have to synthesize a larger antenna, and that's done by the motion of the spacecraft over a period of time. And typically, the spacecraft will travel a few hundred meters, and so simulate an antenna that is a few hundred meters across, correspondingly tens of times better in resolution than the real aperture of the actual antenna. And that works along track or along the azimuth line, and across the track or in range direction, we use timing of the beam to tell us where it's come back from. So to measure in distance across the track, we measure very accurately the time of the signal coming back to us. And so the beam has to look off to the side, because if it was looking straight down, something coming from the left and the right would have the same time signature. So to eliminate that effect, the beam has to look sideways. And so all SAR systems are side looking, and they either look left or right relative to the motion of the spacecraft or relative to the ground. As the spacecraft moves forwards, the along track part, the azimuth part, is measured by Doppler shift. And that's what these colored lines are representing on this image. And so something that's sent slightly forwards of the spacecraft and picked up as it moves towards it is going to be slightly blue shifted. conversely redshifted away from it. And so we can work out from that where along the track, along the azimuth, the image should be formed. So it's kind of important to realize, I guess, it's kind of important to realize, I guess, that the image is made up of time and Doppler, not pixels on the ground, where we get to pixels on the ground much later. Just a little bit of background about radar systems. I don't want to spend any time on this really. Earth-based systems tend to be large. Well, there are smaller ones these days, but the typical sensors that you might be familiar with, like Sentinel and ERS and so on, are fairly large, what's called phased array systems, and they're very complex but very smart systems, and but they have a number of effects. And one of the things that you need to understand about a radar beam is that the beam that the radar generates illuminates a much larger area than is actually imaged by the sensor. So the sensor will only be interested in what's called the beam width, or the beam, the bore sight of the radar, and probably a smaller patch than that beam width. But there is energy going off in all directions, and we can get bright returns from directly below us, which is called nadir, when we're looking off to the side, and other large features that might reflect the beam back. So we have to be careful of those things. But phased arrays are very smart systems because they can steer the beam electronically, and we can generate a whole set of different data types. We don't have that capability with Magellan or with other radar missions so far at other planets, possibly on the moon maybe. So all we get back is a much simpler, you point it, you get that image back. You can't steer the beam electronically. You have to steer the antenna itself or the spacecraft itself. And why would we want to do that? It's because we have to transmit and receive the signal that's returned. That beam that we transmit has to hit the ground, get to the ground, hit the ground, reflect back and come back to the spacecraft. And that takes a certain amount of time. And what we can't do is image while we're doing that. So we have to image in the gaps in between. And if you look on this funny looking diagram here, this could be for any radar really. It's called a diamond diagram. The red bands are where we are transmitting, so we cannot receive during those red bands. And the key thing to bear in mind is the higher the resolution we want, the greater the power we need to have. And to do that, we have to increase the width of those red bands. We have to transmit for longer, the pulse is longer. And so the swath, or the width that we can image, gets smaller in the gaps. The green bands are where we get really strong reflections from from nadir on those side lobes, and we want to avoid those. It's not impossible to image in them, but it creates a lot of noise or false returns. So that's a little bit of background about the radar itself. Here's two images at different wavelengths and different resolutions from Hyde Park in London. This is central London, really. The top image is a typical Sentinel-1 C-band image. That's about 5 centimeters wavelength, and the image has a resolution of about 14 meters. We'll talk about resolution much later on. At much higher resolution, at X-band, which is 3 centimeters wavelength, we get 3 meter resolution data here from TerraSAR X. And it may not be obvious in this image, but it might be obvious a bit later on in some of the other images. The different wavelengths also are sensitive to different things on the ground, and I'll explain that a bit later on. So they don't carry exactly the same information. All SAR images, however, are dependent really on 3 properties of the ground. The first is slope, and that's because the radar beam itself is very sensitive to the angle at which it intersects the ground. So if it points straight down and comes back again, you get a very, very bright return. So any slopes that are facing the radar, remember the radar is probably looking at about 30 degrees, 20 to 30 degrees off, or maybe even 40 degrees off to the side. So any 20, 30, 40 degree slope is going to be pointing straight at the radar and look very bright. And that's what we can see in this left-hand image here. So those slopes there are essentially pointing at the radar and they look extremely bright. The dark slopes that are on the other side are the ones that are facing away from the radar. And in this case, they're probably shadowed. But you can also get, because the beam is reflected more away, it's also darker even when it's not shadowed. In the middle, the other main effect that we see in radar images, particularly from Venus, is surface roughness. And this image shows an impact crater, and moving away from the edge of the impact crater is an ejector blanket. And that ejector blanket just gets finer and finer and finer with distance. That radar is really sensitive to grain size. So in this case with Magellan, the wavelength's about 12 centimeters. So it's really sensitive to the sort of 4 to 8 centimeter range. And as soon as the grain size drops below 8 centimeters, the image starts to get darker. As it drops below 4 centimeters, it becomes almost black. And that's what you can see in this image. So that sort of average grain size in that ejector blanket is dropping off over probably a couple of 100 meters, but to the radar with a resolution of about 100 meters, that's almost an instantaneous cliff. And so we go from very bright to very dark quite rapidly in that view. And that's something to bear in mind when we're looking at radar images, that they are sensitive to surface materials and surface roughness. And the final image on the right is something that we see in very specific places on Venus, and it's more subtle in other places. But this example of the snow line, as it's called, on Venus mountains at high elevation, is a consequence of the relative permittivity of the materials, or it's sometimes known as the dielectric constant of the materials. And in this case, the bright area is an area that has a very high dielectric constant, much higher than we would normally encounter or expect to encounter. Typically, materials on Venus or on Earth even will have a dielectric of below about 4 if they're kind of loose sedimentary type materials, between about 4 and 8 for most rocks, and maybe 8 to 12 for really iron-rich or unusual lavas, for example. So anything above about 12 is unusual, and the dielectric of these bright areas is around about 100, 80 to 100. So that's really significantly different, and we don't yet know what the cause of that high dielectric is, but it's very noticeable in the radar data. And this is sort of what I was hinting at earlier with the brightness of the surface being, the radar being very sensitive to the incidence angle, the angle at which it looks at the surface. This is the other way of looking at that. As you tilt the radar beam towards a flat surface, straight down, it's very, very bright on smooth surfaces. It's still bright on rough surfaces. But as you tilt it gradually further away, those smooth surfaces start to look dark quite rapidly because they're reflecting most of the energy away from the radar and not backscattering it. Whereas rough surfaces tend to be relatively more constant in brightness because they scatter the information, the radar energy in all different directions. So that as you go from top to bottom on the right-hand graph, you can see that effect. And so rough surfaces tend to look brighter at higher incidence angles. And there's an interesting crossover in the sort of 10 to 25 degree range, where you switch between this smooth being bright, rough being dark, smooth being dark, rough being bright. And so we tend to try to keep the radar images imaged at greater than about 30 degrees so that we're in that zone where that brightness change could be recognized. But in Magellan and in a number of other radar systems, we don't always have the choice of controlling that. And so there are Magellan images that are in the 25 or even the 20 degree range, which look very different, even compared to, you know, lower latitudes where the range is more normal. So there's a variety of things that we need to bear in mind in the radar imagery that we need to make sense of. And one other process which we have no real measure for on Venus, but we know takes place, is something called attenuation. And so with a radar system, some of that energy is reflected back as backscattered energy, but some of that energy goes into the ground. And in a very loose, dry soil or sediment, quite a lot of that energy can be transmitted through the ground and to quite some distance. And if we look at these two images here, the top image is an optical image in the infrared, showing the path of the Nile through southern Sudan, northern Sudan, sorry. And in the lower image, we're looking at a radar image. It's colored because there are two bands, C and X band. And you'll see if you look above the Nile on the right, and a few other places too, you'll see a bright, what looks like quite a large channel cutting across the top. And this is sitting underneath that dry desert sand. It may be, in fact, it probably is a former channel of the Nile, a former path, and Nile meanders around over time. But it's probably actually also still a little bit moist. It carries groundwater at the present day, and that makes it look brighter to the radar underneath that sand. So we see quite a big contrast, and we can pick that up. It's possible that we see these effects on Venus without recognizing them because we don't have the optical equivalents. We don't even have images at different wavelengths that might tell us that at this stage. We don't see a strong attenuation signal, so we don't tend to see things just dropping off altogether, except in a few places like ejector blankets. But nonetheless, we might be penetrating centimeters. In this case, you can see a graph here showing 20 centimeters of dry sand or various moisture levels in sand. And of course, the Venus environment is dry. So you can see at, say, 2 gigahertz, which is roughly where Magellan is, there's almost no attenuation in very dry materials. And so it could penetrate 20 centimeters very easily without us even knowing it, which is something we'll look at when we look at the lander images. And if that is the case, and it might be the case in blocky, rough material, that we penetrate the ground and scatter around inside that and then return that energy back to the radar, we get something called volume scattering. We typically get this on the Earth with things like trees, which is what this little animation shows. But it could be granular, gravelly material, for example, or pebbles and things that have the same effect on Venus. Some other artifacts we really need to be concerned about when we're looking at the radar images are geometric distortions. And this is because the beam is illuminating the ground and receiving that signal back under the same system. So we don't see the geometry of the ground as it is. We see the geometry of the ground as seen in the plane of the radar. And so what that means is, because we're looking in time, if there is something that is, say, high on the ground, and we think it's going to be on that nice smooth ground surface, and it's maybe, you know, a kilometer or two high, it's a mountain or something, we're going to place it in the wrong place with respect to the radar. We're going to think it's closer to the radar than it really is, because in time it is closer. We're seeing a peak. And then, so unless we know what the topography is through some other means, we will place the image in the wrong place. And you can see that effect here. Let me just try and get my on-screen laser pointer. That's it, I think. So you see this peak here, this shape here in the image. This should be placed about here, because this is a mountain next to one of these, I think this is Denali, in fact, next to one of the glaciers in Alaska. And in this case, the image is, the scene is being imaged from the top. Normally with Magellan, we're imaging from the side. So everything, it gets slanted that way. But you'll notice a few other effects as well. So that's layover, where the top of the mountain is placed in the wrong place altogether. But you'll notice if we look across the valley, all of these slopes here, which are sort of pointing towards the radar, tipped in the direction of the radar and look slightly dark, these are being extended in effect because they're sloping away from the radar, They look darker because they effectively have an even higher incidence angle than the ground would do, flat ground would do. But they're being sort of stretched out because the peaks are being pulled towards the radar because they're closer, because they're higher. Whereas on the opposite side, the peaks are being pulled towards the radar in exactly the same way, but that slope now has to sort of shrink into a much shorter space. And so it gets foreshortened and it looks much brighter. There's another little layover peak there, and there's a number of others that you can see sitting on what looks like they're on top of the ice there, don't they? So these are some effects that we can see in the radar imagery that we get from Venus. Right. One other thing that we can measure on Venus, and Magellan did measure on Venus, that we tend not to have on the Earth because there's many other effects on the Earth that mean we can't directly measure it, is because the surface of Venus is very hot, 750 Kelvin or so. It emits in the microwave part of the spectrum. So if we just turn off the system and leave it to receive, what we get back is an image of the ground surface generated by Venus's own brightness. And variations in that brightness are dependent on principally on the emissivity of the surface, or the reflectivity, the inverse of the reflectivity, if you like, of the surface. And so this is a useful parameter for us to measure. And it's related to the dielectric constant, if you remember that. The higher the dielectric constant, and if you remember, the highlands are about where that 100 is. So you can see they have a much lower emissivity. Conversely, they reflect much more radar energy than the normal surface, which is around the 0.8 level. And that's why those highlands look so bright, but they look low emissivity areas in emissivity data. And that's a very useful parameter for us to measure. And we can do a conversion between using the SAR information and using the emissivity information. We can approximate what the dielectric constant is for the whole surface. And I've generated those data, and I think they're available in a number of places now. The system also had an active altimeter sensor. So it fired a radar, the same radar beam, but fired it vertically at the ground and listened to the echoes coming back and to estimate the distance to the ground. And there's a number of issues and artifacts with that. But it does derive a number of other useful parameters. It gets something called regional slope, which is really slopes on the 100-meter scale. So a few degrees up to about 20 degrees or so is what's measured. And you can estimate from the reflectivity, the slopes, and the emissivity and other data, you can estimate things like surface density and so on from those materials, from those data. So actually for Venus, we have a whole variety of data sets that we can combine together to give us useful information on the surface, not just the image. So this color image here is a combination, which I'll show you a bit later on, of the radar images and the emissivity. And so the blue areas that we can see in this image are low emissivity, and you'll see that they're associated with impacts more than anything else. So there's a small impact crater on the bottom left, and there's a whole blue area around it, which is the higher dielectric granular material that is thrown out from the crater. But you'll see on the right another sort of patch on the ground, which is dark blue. There's no impact crater, but this is actually where the atmosphere hit the ground and stripped away all the weathered material on the ground surface and exposed that higher dielectric, relatively unweathered material below it. And we can see that as a dark splotch on the ground in the radar image, and we can see its emissivity signature in the emissivity data. And I'll explain a little bit later on how we generate that kind of image. First, I want to address the whole issue of resolution. This is, and what we mean by that. This causes endless confusion in radar data compared to optical data. We're very familiar with optical data of the um, pixel size, if you like, of an image, and we think of that as being the resolution of the image. Of course, it's not actually the resolution of the image. We need 2 pixels to see anything at minimum, because you can't see an edge if you've only got 1 pixel. And in traditional photography and in radar, which is a wave system, we use something called the point spread function to understand what the resolution is. And it basically says, what's the smallest distance between 2 points that can be resolved by the radar? I mean, there's some technical issues in there about the full width half maximum minus 3 dB level, etc. How you define that cutoff on the Rayleigh limit and things like that. But essentially, spatial resolution is about being able to see 2 points discretely rather than 1 blurry point. And that isn't just a straightforward function of distance, because 2 very bright objects, you can do this with your eyes actually, 2 very bright objects can be resolved at much closer distances than 2 dark objects. And so it is dependent not just on the spatial separation, but also how bright those points are. And that links into radiometric resolution, which is really how much information is there in the image that comes back. And it's kind of partly a measure of what's called speckle noise in the system. But speckle is actually a useful parameter. You know, we think of it as noise, but actually it's telling us something about the scattering properties of the surface. So I tend to like to leave it in. Boring, but you need a few looks to smooth it a little bit. But the radiometric resolution will always increase with the number of looks, but of course you lose spatial resolution as you increase the number of looks, because you're averaging more and more images. This is different to sensitivity. So sensitivity, or noise equivalent sigma 0, is a measure of the system noise and various other noises that make up the image. So it's the darkest surface that can be resolved, below which you just see noise. And so the lower that number, the more sensitive you can see, the darker the surface you can resolve. Clutter is something entirely different, and it is to do with other things in the image that you're not interested in. So, you know, if you've got a scene with lots of boulders and things like that, it looks very noisy, and that's frustrating because you want to see where the edge of the lava flow is or something. But of course, somebody else might be interested in those boulders. So clutter is one of those funny things where what's to you an unwanted noise might be to somebody else an important signal. So putting all that together, this is just a nice little overview, really, of the sorts of things you can see. And this is a full polarimetric, tri-band polarimetric image of Pembrokeshire, courtesy of Airbus, and you can see a number of different features within it. But the thing I want to point out that illustrates some of the vagaries of radar data is you can see a bridge up on the top right, above all those boats that are in the river there. And next to the bridge, you can see a whole set of streaks. And they are cars moving across the bridge. And because they are moving, they have a Doppler. And so they are placed in azimuth in the wrong place. Just as with range, we miss time because of the heights of mountains and things. If something is moving, it will appear in the wrong place in azimuth. And that's what that image is showing. But you can see a whole variety of other artifacts in there and features. So I leave that to you to enjoy it in your own time. I'm going to gloss over slightly a few other things that we can do with radar that we can't at the moment do on Venus. Hopefully one day we might do. The first of which is interferometry, because it's such a powerful and important technique on the Earth, and we use it to measure all kinds of different features. So that phase component that I mentioned right at the beginning, we tend to ignore because it just looks like noise. You can sort of see some features in it, but it doesn't mean anything. But when you put the two together and you subtract one from the other, frankly, some magic happens, and you see phase differences. A lot of places you see nothing at all, just noise, and those areas are decorrelated. But in many places you see a pattern, a color, which we can color to the phase. And in most places, that is just an atmospheric effect. We can see these long wavelength features. But sometimes we see these bullseye-like features, and these are places that have moved between the sets of interferograms. And in this case, this is an earthquake that has shifted the ground. And each of those rings is a half wavelength, so about 3 centimeters on the Earth, 2.5, 3 centimeters on the Earth for C-band. And so you can sort of add those up and work out what the displacement is. We do that in the most sort of simple way by something called differential interferometry. So we look at 3 sets of interferograms, or 2 where you've got really good knowledge of the topography, and you look at the phase differences between them and you unwrap them. And then you can work out the displacements in the ground. And that's proved very useful in detecting ground motion on the Earth. This is an infrared image of the Darfield earthquake in Christchurch in New Zealand, about 2010. And there are the displacements and the fault lines shown in the infrared image, quite difficult to see, whereas in the radar image, we see very clearly all those displacements associated with the ground motion. And actually going right out across the whole far field, we can see all these displacements. So we can see about 5 meters of offset in total across this earthquake when we unwrap it. And then moving on into techniques we use really exclusively on the Earth. We'll almost certainly never get enough repeats at Venus to do persistent scatterer interferometry, but the ground scatters in 2 different ways. There are points on the ground that are very bright, like the corners of buildings and things like that. And there are blocks and things on the ground that scatter in a very diffuse or distributed way, but both are persistent or permanent. They're always in the same place. And so we can use them to eliminate things like atmospheric noise and motion, to improve our interferometry by stacking a whole load of them together. And you need about 20. And I think even at our best on Venus, we're never going to get to 20, not in my lifetime anyway. But it's a very useful technique on the Earth and helps us learn more about how radar data works. And that will be useful for understanding Venus data. But it also gives us a chance to compare things on Venus and Earth. This is an example of some of those persistent scatterers on the ground across some buildings. And in this example here, we're looking at a road in London, and we're looking at the displacements of various buildings along that road. And you can see that there's a general sort of substance, which is to do with tunneling in the area, or groundwater movements or something like that. But you can see the odd spikes and other things, and not each, and differences between each one, because some buildings respond differently to those ground movements than others. So it's a very useful tool. The final thing I want to touch on before we go to a break is to get back to those nice color images that I showed you. And for this, we rely on something about the nature of the radar data, that it is sensitive to slope as well as roughness. And that dependence is dependent on instance angle. This is a diagram that I think you don't really need to make much sense of. All it's really saying is rougher surfaces are brighter than the average. The average is the line in the middle going through this. And they're brighter, and they have usually shorter correlation lengths, so that they repeat more rapidly. That's not always true. So turning the clock right back, early Viking days, early lunar data, early Venus data with Pioneer Venus, what people used to do by hand was take all these complex images with their funny illuminations and all their artifacts and issues, and generate airbrushed versions of them, literally airbrush paintings of them. so that you could interpret them with more reliability, because the illumination is constant and someone's taken all that time and effort to make sense of them. Well, that's a very laborious process, but it turns out that you can do this almost automatically in a radar if you have opposite look directions. And the reason for that is that when you look from opposite sides, the slopes effectively cancel out, and what you're left with is roughness. And so if you invert the opposite look, you add together the two slope informations and you eliminate the roughness part. And that's what Randy Kirk at USGS worked out early on in Magellan. And I think this is the only paper I've come across which makes use of that technique in their research. But this is effectively a shaded relief map generated directly by the radar. The problem with it is that in very few cases did Magellan look at the same angle from the right and from the left. And so you end up with artifacts generated by different foreshortening and other features like that, different brightnesses and so on. But here's an example to show you sort of taking it one step further. These are two images of Atla Regio and on the left there you can see Map Mons, and at the top you can see forgotten the name of it now. Anyway, the big volcano up there, and they look similar, but there are subtle differences. There are some artifacts, of course, but as much as anything, you can see different illuminations from different directions and some subtle differences in the surfaces. So when we combine them together in the traditional way, we get a shaded relief effect, which we see on the left here, and I've partially corrected for the differing viewing geometries. And then on the right, we've added together, so this is just roughness. I've colored it with a funny color table, and now there are much more sensible color tables that you could use actually. And combine them together, actually we've got the same two images, but because we've combined them in a different way, we are getting visually more information out of it. We can see more into the image than you might do in either of the two grayscale images. And that's because we're very sensitive to color. So we can see the shading, we can see the color. It works perfectly on the Earth because our radars are much more controlled. So this Sentinel set of images from Iceland, they're exactly the same incidence angle from opposite directions, or almost opposite directions. And so the effect works beautifully. So you can see what it looks like. And the reason I show this is actually to highlight the fact that the radar image is composed of slope and roughness. You'll notice that in the center of Iceland, across the middle part, there are a series of blue areas that look like the sea. Those are ice areas. They're very smooth. The darker the blue, the smoother the surface. In fact, the lighter the blue is waves on the sea and is sort of rough surfaces, snow surfaces on the ice. And they look very different, but similar to each other, but they look very different to the rough surface of the ground, which is gravelly and so on, with all the volcanic pumice and things like that that's lying around. And so you can see those subtle differences in color picking out surface roughness, and those slopes, the shaded relief part of it, picking out the slopes and the topography. And that's very powerful for us to use and can help us make sense of it. So my other example here from Venus, which is an area where I was mapping something called Scathach fluctus, which I'll talk about in the next hour. You can see it in the middle there. It's the sort of bullseye effect. You can see a whole load of other features as well, impact crater and lava flows and rifts and other things, but it's all grey, as my students would say about rocks. And when we generate the left and right components, and in this case, I've added in also the emissivity component, which is giving you the blue shading. We can actually see areas that are smooth and high emissivity in the sort of dark blue areas, and areas that are moderate roughness, moderate emissivity in the green, and areas of relatively intermediate or low emissivity, but very rough surfaces in the pink. And we can sort of separate these out and interpret them much more easily. And we can actually see and distinguish features like the pyroclastic flows because they are different in roughness and the emissivity, stretching out, enhancing it, we can see that much more clearly on areas where in the grey image we can't see it at all. So the part on the left is very obvious in the grey image, but the part to the south, to the bottom, is not so obvious at all. You can sort of subtly make it out, but it's much clearer in this pattern here. So there's a sort of a range of things that we have to keep in mind when we're looking at radar images and make sense of them, really. And then we want to also bear in mind the techniques we can use. There's some things that can be really helpful with radar data, but we must remember radar is sensitive to slope and roughness primarily, and only secondarily really to surface materials. So that's something we'll bear in mind when we look at Venus in the next 45 minutes.